Hello everybody, today we are going to be making the game of life for the LED grid. Just go ahead and start out by importing LED. Now if you have the LED package in your site's directory, this should import just fine. If not, you can go ahead and go to the GitHub and get the LED folder with the package in it and put it inside of your working directory. So from there, let's go ahead and do led.draw. And so what this will do is just flash up a window real quick, and this will show us that our package has been imported correctly. There we go. Now if we want this to stay open, we're going to have to throw that into a while true loop. And there we have it. Now I actually prefer to import the LED package like this. So from LED import asterisk, and what this will do is remove the need to append LED dot to the beginning of every function from the LED package. And so now we can just write the names of the functions directly. Let's go ahead and set the orientation to be landscape mode. And so what this does is rotates display output 90 degrees. And so now we'll end up with the LED sim showing that this has now been rotated 90 degrees and is in landscape mode. From there, let's import numpy as np. And we're going to make our grid using a numpy array. The reason we're using numpy is it can process in parallel and it's much faster. This is kind of unnecessary, but I think it's a really elegant solution compared to the default Python arrays method of doing the game of life. So let's go ahead and do world is equal to numpy dot random dot randint, that means random integer, and we'll go ahead and fill the grid with numbers starting from the low end at 0 and to the high end as 2. And so what this actually means is from 0 up until but not including 2. So that's 0 or 1. So fill a grid with random 0 and 1s. And now we need to specify size. So we'll do that up here. And for now we'll start with a size which is set in a tuple of 4x4. And this is just to show kind of the logic behind the game of life. So we're going to be using a smaller grid at first. Let's go ahead and print the world, and what we should see is a 4x4 grid of 0s and 1s, and there we have it. Now we need to make an array to keep track of the neighbors, and so what we're going to do here is neighbors is equal to numpy dot zeros, and so that will make a numpy array full of zeros instead of the 0 or 1, and we'll set that to the same size. Let's go ahead and show what that looks like. And you can see here, just zeros, and I spelled that wrong, so let's fix that. Actually, we don't need to keep printing that. So from there, let's go ahead and actually make this draw the cells. So let's do LED, well, for row and world, print the row, go print some text, and what we'll see here is that this is going to print every single row of the grid separately. Yep. So now for every single row within the world, we're going to take the cells for cell and row. And now we can do draw pixel, or draw point actually. Let's do X and Y and enumerate. What this will do is it will count the indices as we go up and then also take the values from that array. So now what we can do is draw XY. Well, actually here. Let's change this to life. And so that will be getting the value of every single cell in the row. And if life equal 1, so if it's alive, we'll draw a white point at the given X and Y. We'll just do white. LED comes with constants or colors. Now we can see up here, it has drawn our grid. Let's go ahead and blow up the size of this grid to something meaningful. Let's do get width adjusted, and what adjusted means here is that it's adjusted for the orientation. Without that, it's always going to take it assuming that you're in orientation 0. And then we'll do get width, get height adjusted, throw that into a tuple, and now we should see that it covers the whole screen. There we have it. Now here comes the logic part, which I'll briefly explain. Let's go ahead and do neighbor calculations here. And then updating the world accordingly. And I'll do a brief explanation of how the game of life actually works. So for every cell in the grid, it has a number of neighbors, and we'll represent those neighbors in white here. And so for this cell, it would have 3 neighbors, counting all the 8 cells around it. And so what we need to do is we need to do that for every single cell across the entire grid. And so these will be counting to their right and up and etc. How we're going to do that is using a numpy function called roll. So let's go ahead and look at what that means. Let's go ahead and do np.array, and we'll make an array of just ABC. And this is just to explain. You don't actually have to type this if you want to do the game of life. Let's print that. Let's call that ABC. Print ABC. We got ABC right here. Now, if we roll this, np.roll, if we roll that 1 to the right, this is a one-dimensional array, so we don't have to specify which direction. And we'll just assume for negatives that you're going to the left, and for positives you're going to the right. What we should see is it will spell cab, C-A-B, and that's because it took this and rolled it over to the other side, right here at the start, and then move the other ones accordingly. So what we'll need to do is roll the grid to the right to get this one, to count that neighbor if there is one there. So we'll go ahead and specify a few neighbors here. We need to roll it down so that it will count it. We need to roll it to the right and up so that it will count it, and so forth. And what we'll be doing is, since this wraps around, we'll also be accounting for cells that are on the other side of the grid. And so when we run the simulation, we'll see that sometimes the game of life will spill off the side of the screen and reappear on the other. So let's go ahead and do neighbors is equal to, and what we'll be rolling is the world itself, np.roll world. Roll this one to the right one, and then we do need to set an alignment, or not an alignment, an axis equal to 1, 1 being the horizontal. And so that's what that's going to be doing, is moving all the cells this way, and then we'll be adding that. Okay. Get plus here, so count left cells. -1. This is how we'll count the right cells. Change the axis to 0 for the verticals. So now that the axis is 0, we're counting things vertically. Do the same thing. So this should count count top cells, count bottom cells, and something important to remember is that within computer graphics, the y-axis goes down. An increasing y will point down, and a negative y will point up. Now we need to count the diagonals. So we'll just call that like northeast, northwest, south, east, southwest. And something kind of tricky here is we're actually going to have to specify two axes that it works on. So 0, 1, 0, 1. Oop, let's do that in the tuple correctly. 0, 1, 0, 1. And get rid of that plus. Now we need to make these tuples as well, so the coordinate for the shift. Let's go to the right and down one. Actually, we'll start at the top. So this is the northeast, northwest, right. Man, braining this is hard. We actually have to move that up one. If we get these wrong, we'll just pop back in and fix them. And then for the southern points, we'll have to shift it down one. I'm going to realign these pluses, because why not? Makes pretty code. So in theory, that should work. Let's go ahead and see though. I'm gonna bring this down to something reasonable, like 4x4 or 5x5. And we're gonna print the neighbors. And we'll see if it counts them correctly. Well, we should print the world first though. So print world. Let's not actually do that in a while loop, just for the moment B, so it only prints once. So let's see, this one right here should have one neighbor. Okay, so we messed up by not including this. So let's see, this right here should have 1, 2, 3, 4 neighbors. We go down here, 4 neighbors. This right here, 2, 3, 4, 5, 6. And so we go right here and we see that it's 6. So that is working correctly. Now the rules for the game of life is that if there is 3 neighbors, I'll actually start with the simpler rules. If there is less than 2 neighbors, a cell dies from loneliness. If there is greater than 3 neighbors, a cell dies from overpopulation. If there's 3 neighbors and it is alive, nothing happens. If there is 3 neighbors and a cell is dead, another cell is born there. And so, rather than do a bunch of if statements, we can actually summarize these rules into something more concise. So what we can do is world n equal neighbors equal 2. And then what this will do is if neighbors is not equal to 2, let's say in the case that it's less than 2, this will be false, and equaling that cell in the world will then make that cell equal to 0, which is the state of being dead, and so a cell dies from loneliness. In the case that it is greater than 2, it's going to also die unless it's caught by the next rule. World equal, or equals, neighbors equal to 3. And in the case that it is equal to 2, of course, an and equal, if that cell is already alive, is that it stays alive and continues. With this or equal rule, this covers these latter 2 rules, in that if there's already a cell there and or equaled with true will of course make that cell still alive. And in the case that there is nothing here, as in that cell is dead, an or equal with true will have that cell reborn. Interestingly enough though, with this, it in theory kills off the cell every single time, but that's not actually seen by the iterations itself. That's just there in the logic. From there, we can run this, but I just realized we forgot to refresh the screen. I'll go ahead and show what happens if we don't. We'll just end up with a bunch of white. Right, so it fills the screen without ever refreshing it. We need refresh to fill the game screen with black for every iteration of this, and we will end up with the game of life. And there we have it. Let's see, from here we can do some fun things like change the color, change the background color, we do not need the LED dot. What should we do? I don't know, brown. And there we have it. Another thing to mention is this is a little bit terse and difficult to understand why this works. I should have mentioned that. So this is equivalent to saying for row in world, for cell in row, and then we'll do cell and equal neighbor of this same location equal to. And so numpy will take arrays and compute them in parallel as if they're single variables. And so that's what this is doing, and that can be a little bit difficult to understand. Or just envision this as basically the same thing as this, except for now we are doing comparisons. Alright, thank you for watching, and I hope that was a comprehensive and useful tutorial.